What we have is the ECU hardware, the electronic control unit. This is the domain controller. And on top of that, then we have the software, which is structured into different layers built on top of each other. The lowest or the lowermost layer is the operating system, or the board support package, as it is called. So this has all the core components that is needed to fire up all the sensors on startup and so on. Then on top of that, we have something known as a middleware. Mm, As an example, these days, a lot a middleware known as a robot operating system, ROS, and as well as the next generation of ROS 2 is present. We also have other middlewares from called as ADTF from a German OEM. These things acts as a gluing layer between the information exchange between the lower layer and the application layer. And then on top comes the application layer. Here is where we have different modules, different applications itself, such as the driver assistance systems, system features that I mentioned. Let's say lane keep assist or a traffic jam copilot. The software that is needed to program these is what resides in the application layer. And this is how the information exchange goes up and down through these different layers. We will have actually a much better look in understanding how the software is from this diagram. So here you can see that the input is coming from the environment. So assume we are driving on a highway. It's a 3-lane highway. We have cars around us, and we have different sensors. So the sensors are of two types. One is active sensors, which is LiDAR, radar, because these are actually emitting some form of waves, and then once they reflect or hit some object or target obstacles, they receive it back. Hence, they are active sensors. And then we have the passive sensors like camera. So the environment, what we are trying to do is sense, like even how we do as human drivers. So we are always using our eyes. We are seeing who is driving in front of us. Is there a car in the lane next to me? We are trying to make sense of this information. That is the stimulus that is coming from the environment. Other than these traditional sensors, we also have maps that we use in navigation. So we have the standard definition maps, high definition maps, also GPS information to know where exactly we are in a given driving environment. All the information that comes from the environment is captured through sensors, and some kind of pre-processing is done to pass it on to the next layer. So the next step comes is what we call as the perception layer, where we are trying to bind or fuse together the data from all these sensors, and then have an idea about, or I'm basically representing the environment around myself as a model, where I know that at a given XY location in the world, my car, and I know how far the other objects are, at what speeds they are traveling. So all this information is deduced using some perception algorithms. The next step then comes in the planning layer or the decision layer. So this is where, again, we have some predictive algorithms, which is trying to do, like, it's trying to work out all the mathematics involved in, let's say, we want to overtake a car that is driving in front of us. It's slow and we want to overtake it. So in this case, we have to make a lane change maneuver, and this prediction to make a lane change is what will be done in this planning layer. And once this path is predicted for the lane change, then comes the final layer, where the actual control signals. So we have a reference that I have to follow this path, and then the control layer is what actually will make the end effect. Calculate the steering angles, calculate the amount of acceleration that is needed in case of overtaking a car, or in another situation, let's say the car in front of us is breaking down, starts to brake, then we have to judge this and accordingly also apply brakes so that we avoid collision. So this is how the software actually looks like. Then we now move towards the part of the case study that I had mentioned. So these are the advanced driver assistance systems, which, as I mentioned, is kind of a stepping stone to proceed from level 1, level 2, slowly towards 3, 4, and 5. So in this image, what you see here are different small assistance systems that is present in even in cars today. So we have an adaptive cruise control. This is a feature where we are in cruise mode. So in a highway setting, let's say we have a speed limit of 120 kilometers per hour. You have an option on a button, so you just set a speed 120, and you can always free up your legs from the accelerator pedal, and the car is driving at 120. It will always try to maintain the speed. In case if the car in front of us is breaking down, this system is intelligent enough to actually guess that, okay, the car in front of me is breaking down, and it will try to adapt its speed. Even though we've set a speed of 120, if the car in front of us suddenly, say, slows down to 100 kilometers per hour, our car can sense this and then adapt our speed and slow it down to 100. And it will always try to keep a safe distance of 2 seconds or 3 seconds based on the requirements to keep following the lead car. Then another such system is the emergency braking system, where in a city environment, let's assume that suddenly a small kid who's playing comes in front of the car, or a pedestrian or cyclist comes into the path of our car. In slow situations as well as highway situations, the car can then act upon this. It will detect that, okay, I might possibly collide into this object or into this person, and already the reaction time that humans need is actually a bit higher. But since these sensors can predict them in advance, that, okay, a possible collision is possible, it can pre-fill the brake pressure systems and also apply the brakes for us in some cases. Then the other systems, such as lane change assist and also the blind spot detection, is where on a highway situation, if we are driving and we want to change our lanes, is these two features actually work in combination with each other, because when we are making a lane change, we have to always ensure that we don't have a car in the blind spot zones of our car, and only in such cases it's safe to make a lane change. So we have radar sensors, which is actually monitoring the blind spot zones of the vehicle. And in case if there is a car present in it and we turn on our turn indicators, then the system actually starts warning us that it's not safe to make this lane change. And because I've detected a car in the blind spot zone, and once this car is not present, then you can continue to make the maneuver. And apart from this, we also have intelligent parking assistance. Like I mentioned, there is already a project going on between Bosch and Daimler, where they have a smart summon feature, where they also have a complete parking feature developed, which can work independently. So you arrive at the entrance of a big parking lot, get down of the car, get down, and then using your app, you can see which parking spot you want the car to park in. And then the car is completely capable of driving in completely and parking the car at its spot. So I hope you have at least some sort of an idea about how different, like what are the different driver assistance features. And what we can actually do is take some of these combinations and then actually build up a more complicated feature of level 3 or level 4. Let's say, for example, the traffic jam copilot. This is a feature which works from a speed range of 0 to 60 kilometers per hour in traffic situations, only on highways. And here what we can do is we can take the software from adaptive cruise control, because it's a traffic situation. We have cars in all three lanes, and we can always keep following the lead car. We also have the lane change assist, or another driver assistance feature, which is the lane keeping assist. So let's assume we are driving in the middle lane. This feature will help us to always, it ensures it's continuously monitoring whether we have crossed over the lane lines or not. And in case if we are crossing, then it tries to bring us back into the center of the lane. So we can combine all these features. So, or let's say if the car in front of us suddenly is driving at 40 and then suddenly slows down. So we can use the emergency braking feature as well to slow us down. So it's actually a combination of these small independent features that can be utilized, that can be fused together to build up more complicated systems going on towards bridging towards level 3 and level 4. Like I mentioned, a traffic jam copilot is a level 3 feature, and it is capable of independent operation in different traffic scenarios. It's mostly in access controlled highways. In US, it's the motorways or freeways. In Germany, it's the autobahns. And what we are doing is always we are utilizing these features from subsystems and always following the lead car, and it's a relief for the driver, at least for the time being of the when traffic situations have built up. And once the traffic is over, so the congestion is getting free, it will ask the driver to take control back as of now, because like I mentioned, it's a level 3 feature. And going ahead, definitely we will also have more level 4 features, which is capable of much more complex operation. So until now, I guess you have a good idea about how interesting this field is. It's actually quite challenging because there are a lot of technical capabilities that have to be still have to be overcome. And to get into this field, it's actually there are a lot of skills which is needed. For example, after bachelor's, you can definitely get into, for your master's, you can study core electrical engineering or a combination of electrical and software engineering, or even these days we have mechatronics, like I mentioned. So it's a combination of mechanical engineering, electronics, as well as software. You also have the possibility to specialize yourself in robotics. So especially in mobile robotics, that's actually even what I have specialized in, because the application of autonomous driving is more of an extension of the field of mobile robotics. And that's why studying something like this is also definitely useful. Other than that, it's quite essential in today's world, especially if you want to enter these fields. It's important to have some programming background, Python, C++, as well as MATLAB, Simulink. Um, C++ is still required. Actually, even in cars, it's pure C. But these days, even a lot of emphasis is given on MATLAB and as well as Simulink, because we have so many tools being offered from these companies, such as automatic code generation. We have a lot of other tools, which is quite useful, and it has more robust code than humans actually writing programs. Additionally, we also need to know different new and upcoming fields. We have algorithms from machine learning, deep learning, which actually make up a lot of the part of the sensing part as well as the perception part. Also AI, surely. Other than that, we also have robotic frameworks. So as I mentioned earlier, we have something known as robot operating system these days, and the latest version, ROS2, which is actually being adopted a lot, especially in the pre-development projects by a lot of companies, even traditional automotive companies. So I know for sure that companies such as Daimler and BMW also are using ROS2 extensively, at least in the pre-development project, maybe not in series production, but as a research, definitely this is being looked upon. And if you have knowledge about these tools, then it's an advantage to get into this field. So having known about the different skills that you must acquire, these are the different career path and opportunities that you can get into if you are willing to enter into this field. So you can work as a robotic software engineer, you can work as a self-driving car engineer, and a lot more. And it's actually not limited only until development. So it's not like we would be core software developers, because as critical as development is, but it's also important to test what we are developing. So as testing, we have different environments. So we have to test the software, we have to test the hardware, we have to test both of them working together. And then there are a lot of other concerns as well. So we have safety requirements, we have also performance related requirements, and then making the software so robust that it can function in different weather conditions, in different countries, different driving conditions. So we have left-hand drive, we have right-hand drive, and so on. So these things might sound very trivial, but when we are actually trying to implement them in the cars, it's quite challenging. So it's also quite interesting actually to work as a software test engineer be it at different levels. So you can either test the entire system, or maybe you test some small parts out of it. And other than that, if you are interested core in fields of machine learning and AI, you have a lot of small stacks within these software parts, like I mentioned, in perception, environment modeling, or even in behavior prediction, and then planning the motion path prediction. All these things I can say is an independent field in itself, and there's a lot of research that's going on. It's quite interesting to work in as a motion planning engineer, for example. I think taking this course will definitely expose you to more of what's going on actually in the industry, because in academia we are quite restricted to getting basic knowledge, but it's important to actually also have an idea about different tools, different methods, and also frameworks, software frameworks that is being used by the industry actually in series production, as well as in pre-series or pre-development projects.